We want to welcome you to Param Hansa Philanthropies' very first Quantum in Bio conference. Give yourselves a hand. You're a part of it. Wonderful. Today is just the beginning.
So much fun to really explore. Like, what does it mean to really bring things together but make it bigger than what the individual fragments were? We're trying to do this in computing, in software, in business software, in many things in life. We just have ended up fragmenting a lot of experiences. And what happened in the last 300 years is that we said we got to specialize, we got to specialize, we got to specialize. And what we've ended up with is a bunch of boxes, lots of boxes, and we box people into one thing and the other. We need an industrial revolution in the world of quantum. One of the biggest investments we can make is in improving life. Can we be mindful in the way we actually not just learn and lead, but also get to know each other and understand where really the next 3, 5, 10 years are going to be, is basically the idea of giving. Quantum in biology, it's really a play on words as well. It's not just technically quantum. It's about making quantum leaps in biology, in cancer research. As a bunch of researchers actually come together and really think about those things. I think that's the whole goal of this conference and this getting together of people.
Our first program is about insights on the last decade and the opportunities ahead.
What would a quantum computer be good for? How long until we have useful quantum computers? I now see it as a live possibility that we'll have a fault-tolerant quantum computer running Shor's factoring algorithm before the next US presidential election. This little quip I made sort of went viral on Twitter, and people were saying, Aronson says quantum computing by 2028, this means you need to buy stock in IonQ. Is the next question that I very often get, which is, what would a quantum computer be good for? What everyone wants to say is that a quantum computer is just the next faster computer. It just speeds up everything by just trying all the answers in parallel. Unfortunately, that is not how it works. So it's something weirder than any science fiction writer would have had the imagination to invent. Quantum computing seems to give dramatic speed-ups over classical computing, mostly in two pretty specific application domains. Okay, the first one, famously, is breaking almost all of the public key encryption that currently protects the internet. Okay, and the second big application is simulating quantum physics and chemistry themselves.
We focus on drug discovery and therapeutics. So after about 17 years in US universities and national labs, including Lawrence Berkeley National Lab and SLAC National Lab, where I was for 8 years, I started my first drug discovery company in 2015, which was a platform company using high-throughput X-ray crystallography. And then that led on to some compounds that we developed. That led to starting the second company, Exposed Therapeutics, for which we were thinking of setting up through a secret application in Texas, but we did not do that. We ended up getting funding from NCI.
You can still come back to Texas.
But interestingly, in 6-7 years, we have made a lot of progress in DNA damage response in the company, and the company is now under acquisition. So this is something very new.
Congratulations.
So I'm happy to talk about this entire journey of labs, academic science, translational research, government funding, startups, entrepreneurship, and bringing things together. In the last couple of years, I've been trying to think about, the more I study cancer and look at cancer biology, it's really the opposite side of aging and longevity, for which there's a big focus now, right? Writing a paper is really branding and marketing in some sense, but we do not think about that either. Funding applications are pitching to investors, which is the public, NIH. So it's all there. All the elements are there. We just do not think about it like that, and people do not think about it in terms of how to extend that into the real world, right? But it can all be done fairly straightforwardly. And many universities are now, of course, promoting entrepreneurship and incubators and all that. So I think these things are coming into force. The biggest impediment probably is just the ability to convert into a business use case, right?
Yeah, when I started my lab, we were a little depressed because pay lines had dipped under 20 percentile on your grant application. And it's like, oh, that's so hard. And this past year at the National Cancer Institute, the pay line dipped to 4 percentile. That's really depressing. So I think my timing of moving into funding science, pretty good. But this is actually a challenge for us at CPRIT is how do we keep the pay lines up? This year we have individual research grant awards, 3-year grants, $300,000 a year. And the pay line, because we have 515 applications, the pay line's only about 8 or 9 percentile. So only the top 8 or 9%. And of course, it's when you're looking at the curve of the scores, 8 or 9% gets about there, and it goes really high up. So it's very hard to draw a line and say, gosh, we can't fund a bunch of really good grants. And although we have a lot of money, $300 million a year, that amount hasn't increased in 16 years. So we've been hit by inflation pretty hard.
Are we in the 50s or the 60s of where the classical computer was when we think of the quantum computer, or do you think we're in 70s?
I think that we're at least in the 40s. I mean, I think that, you know, we can see like the at least barely the transistor, you know, the basic building blocks that we're going to use to scale. You know, we've just started. I mean, one thing that makes the comparison weird, right, is that this time around classical computing already exists.